and the concepts of static friction and kinetic friction. It's always harder to get something moving than it is to continue it moving. We looked at why friction is what it is, the interlocking between surfaces as they slide past each other. And then this is as far as we got because I didn't want to give you the equation yesterday. So, when we were discussing friction yesterday, we said that friction was dependent on a couple things. We said that friction was dependent on the mass of the object that's sliding across the surface. That's mostly true. We also said that the force of friction is dependent on what the surfaces themselves are, and that's also completely true. And so we have to figure out a way to work those out into an equation. And so the equation is going to look like this. Force of friction we denote with a capital F for force, lowercase f for friction. And when calculating this thing, there are two concepts that we bring in here, Fn and mu. When we talk about the mass having a role in friction, the temptation is to say, yes, the mass is connected to the force of friction through gravity, and that's actually not the case. Gravity pulls down all the time, but grab an example here. If I have this desk here, and I put some masses on it, each one of these masses should be half a kilo, so 1.5 kilograms sitting on top of that mass there, and I want to pull on this thing. Wait, I'm using Raina's desk. I don't want to use Raina's desk anymore. No, you need to use the desk. I'll go over here and use Jaden's desk. Because he doesn't use it for some reason. And we go over here and I pull on this thing. It requires, a certain amount of pulling for me to make this happen, but if I take those masses off, it's a lot easier for me to drag the little block across the table. What if I incline this thing? What if I take this thing and I incline it? Now, is it going to be easier or harder for me to pull this thing down the incline? Probably easier, because what's helping me? In some way, gravity is helping me pull this thing down here. Likewise, if I did the exact opposite, and I tilted this thing back and I pulled this thing up, it would now be harder for me to pull this thing, but gravity, because gravity now is kind of pulling down the thing. So it's not just mass connected to gravity, it's mass connected to how hard this surface that we're on is pushing up against this block. And so it's not Fg that we're concerned about, it's what? What is the force of the surface pushing up against this block? Friction is what's pulling back against me as I pull the block across the surface. What is the name of the force responsible for pushing up on this block from this desk? The normal force. And I can reduce it, right? If I reduce the normal force, it's going to reduce the amount of friction. If I start to angle this thing, the normal force is going to get less and less to the point where this thing, if I increase the incline all the way, what's the normal force between the block and the desk? 0. The normal force here is a maximum because remember the normal force is perpendicular to the surface. So it's not. It is mass, but it's not mass. It's not mass in the fact that it's not force of gravity, but it is mass in that most of the time, for most of the scenarios we look at, the force of gravity is equal to Fg for surfaces that aren't inclined. So, force of friction is going to be, and leave a little bit of space here, force of friction is dependent on the normal force. So normal force, or Fn is normal force, we'll fill that in over here. If you recall, this force is perpendicular to the surface. And when the surface is flat, Fn equals Fg. Fn equals Fg, and I'll put the other piece in here, on a flat surface. So part of this is, it's absolutely connected to the mass of the object. The mass of the object is directly connected to how the force of gravity pulls down on the thing, and the force of gravity pulling down on the thing is directly related to the surface pushing up on the object that you're trying to slide across. So that's Fn. The other piece to this that we discussed yesterday is the idea that different surfaces have different kinds of friction it would seem. So I have the desk, and I've got my 1.5 kilos sitting on top of this wooden block, and oh no, I still have it. So as I pull this thing across here, there is a certain level of difficulty as I drag this thing across the desk. I grab the scale, I figure out what it is, but I'm going to. We'll drag it across here. A certain level of difficulty. You know what? Screw it. Let's get the scale. Let's find some numbers. I have them. I may as well use them. To drag this thing across this desk is like 6 newtons of force. But what if it's not the desk? I keep everything the same. Some of you may have noticed that for some reason I've got a metal sheet duct taped to this table. The lab that you're going to do for me today and tomorrow is why. Because by duct taping a metal sheet here, I've now provided another surface that you can drag stuff across. So if I drag stuff across here, how much force is required? Well, the desk was 6. This one is 5. Oh, actually, it's more than that. It's 11. It requires 11 newtons of force to drag the same mass across this metal sheet as opposed to that desk there. And some of you may have noticed that I've got a piece of particle board duct taped to this table over here. If I want to drag something across there, this one only requires 3 newtons of force to pull it across here. Mass was the same in each case, 1.5 kilos plus the block. Over that desk, that sheet of metal, and this piece of particle board or MDF or whatever you call it. And we got a different result in every case. There was less force on that than it was on that, which was less force than on the metal sheet. So there's something about the materials that we use that impacts how much friction is present. And in this expression, we use this little symbol here to represent that changing constant, which sounds weird. How can a constant change? This letter, does anyone recognize this letter? Does anyone know this letter? In Spanish, it's mu. It's actually not Spanish, it's Greek. In Greek, it's mu. This is the Greek, from the Greek alphabet. This is the letter mu. And because it's Greek, anyone who's non-Greek is going to say it the exact same way. It's the Greek letter M in their alphabet. And in other places, this letter represents different things. In physics, mu represents what we give it a name, we call it the coefficient of friction. What do coefficients do in math? You were all introduced to coefficients in grade 9. Where is a coefficient placed in an expression? Dana, you look like someone who knows the answer. No? You're just waving your hand around, then you don't know the answer. Okay. It's the number that's next to the variable. Yes. So like in 2x, x is the variable, 2 is the coefficient. How are the 2 and the x related to each other? Mathematically. Sorry? Yeah, say it. They're being multiplied together. So the coefficient of friction is a multiplier. It multiplies with the normal force. To give you the force of friction. So the normal force is easy. On a flat surface, the normal force is equal to Fg. The coefficient of friction, and I'm going under this equal sign here, this value is dependent, or I'll say depends on, these sliding surfaces. So there are as many coefficients of friction as there are possible combinations of objects that will slide past each other. If you can come up with a combination of surfaces, there is a coefficient of friction for those surfaces. Steel and metal, or sorry, steel and ice, coefficient of friction. Well, maybe the skates are made of wood. You're Dutch, and you're wearing those wooden shoes that they wear, and now you step on ice. Wood on ice, different coefficient of friction. If you start changing the kind of wood, oak versus maple versus cedar versus alder versus whatever, different coefficient of friction. To what degree have you sanded it? Different coefficient of friction. What if I've got different grits of sandpaper rubbing past each other? Different coefficients of friction. So every possible combination of surfaces that exist, when these materials get developed, someone somewhere has to calculate the coefficient of friction for that object and whatever other surfaces it could be interacting with. If you Google these things, there are thousands of them that just exist in tables. And each one of these things has been experimentally verified. Someone somewhere found it out. And it's not actually that hard to do. You guys are going to do it for me. If the force of friction is equal to this coefficient of friction times the normal force, if instead of using it this way, where I know the coefficient of friction and I can measure the normal force, what if I wanted to do it the other way? What if I wanted the coefficient of friction and I knew the force of friction and the normal force? How could I isolate this expression for mu? How do I get mu alone in this equation is another way to say that same thing. Yeah, divide Fn over, and I'm going to get mu equals the force of friction divided by the normal force, which is going to be the lab that you guys are going to do for me. I'm going to give you a bunch of different surfaces. Some of them are out here already. A bunch of different surfaces. You're going to drag objects across surfaces. By dragging them across at constant speed, you know if the speed is constant, you know that your applied force has to equal your force of friction. You can use the scales to measure the normal force because we're not inclining anything here. And you're going to go ahead and you're going to calculate a bunch of mu's for a bunch of different surfaces. Force of friction is equal to mu Fn. Yesterday in the simulation that I gave you, and then we went outside, we talked about the combination of the comparison between static friction and kinetic friction. Static friction we'll define here again. It's friction for a stationary object. And kinetic friction rather is friction for a moving object. I'll put slash. It has to move in a particular way. It has to be sliding. Moving slash sliding object. And you guys looked at this yesterday. Which one of those is always bigger? The static one, yeah. The force of the friction, static friction, is always greater than kinetic friction. But masses being equal, because the normal force isn't changing, it was moving and now it's not. What we're going to find is that the static coefficient of friction has to be greater than the kinetic coefficient of friction. And again, it's part of your lab. You guys are going to figure out static friction and kinetic friction for all of these surfaces. It's going to be great. So let's do 3 examples. Here they are. Example 1. We've got a block pushed along a tabletop with a force of 45 newtons. The coefficient of friction, we are told, between these two surfaces is 0.65. Coefficient of friction is 0.65, and there's a 3.75 kilogram block pushed along a tabletop with a force of this. So we've got, again, as always, the language of the question is important. And when we're doing this whole chapter, first thing we do is we draw a free body diagram. So, what's the free body diagram going to look like for this block? Sorry? You're going to have gravity. Gravity's acting which way? Down. What else? Normal. Normal's acting which way? Up. How do you know it's up? It will balance gravity, but that's not why it's up. What is causing the normal force to be a thing in this question? What's the surface? Tabletop. And as far as you guys are concerned, tables are flat. So by telling you that this thing's a tabletop, it means the surface is not inclined, it is a flat surface, and this is why Fn is straight up. And it's because Fn is straight up, as Rayreet said, this is going to be equal to Fg. As soon as we figure out what Fg is, we're going to know what the normal force has to be. Because for an object that's not moving vertically, these two have to balance. What else is going to go on this free body diagram? There's an applied force. It doesn't say which way, so which way, Jack, do you want the applied force to be? Sure. There's an applied force to the right. We're given a value for that, so let's just put it in right away. Fa is 45 newtons. What else is present on this free body diagram? There has to be friction. By telling you that there's a coefficient of friction that isn't 0, that means friction has to be present. And based on the fact that this block is being pushed to the right, friction has to be which way? Has to be to the left. Friction always opposes motion. So the force of friction is going to be back that way. And that is the complete free body diagram. Interesting. Based on what I'm seeing here, well, that's not useful. Based on this coefficient of friction, just to give you an example of what I mean by coefficient of friction, I just looked up a table of coefficients of friction. By telling you the coefficient of friction is 0.65, that means, here we go. The block could be made of glass, and the tabletop could be made of copper, is one combination of materials that would give you this. Leather wrapped block on cast iron could give you that same combination of coefficients of friction. Zinc on zinc, if this was a zinc block on a zinc table, could give us that same kind of coefficient of friction. So and all these are experimentally verified. So let's go ahead and keep going. We want to find the force of friction and we want to find the acceleration of the object. So we've got some values, we can find some values here. Friction is equal to, let's go below it here, to find friction, friction is going to be equal to the coefficient of friction times the normal force. Always write down the formulas for the things you're trying to find. And we know one of these. We know the coefficient of friction is 0.65, so we can put that in here. And what we need to do now is we need to multiply that by Fn. We don't know Fn, but we know the surface is level. On a level surface, Fn is going to equal Fg. So then to find Fn, we need to find Fg. Fg is going to be equal to mg, because it's presumably the table's on the surface of the Earth and not orbiting the Earth. That would be weird. The mass of the object is 3.75, and the acceleration due to gravity on or near the surface of the Earth is 9.8. So what that's going to give us is a force of gravity of 36.75. So if Fg is 36.75, that means, because this is a level surface, Fn is equal to 36.75. And so now we can go ahead and say, okay, I want to find my force of friction. I can take this value and plug it in here, 36.75. And we're going to find that the force of friction in this particular scenario is going to equal 0.65 times 36.75. For the sake of time, 0.65 times 36.75. Oops. 0.65 times 36.75. I get a value of 23.89. So that is the force of friction caused by this object and the coefficient of friction between these two materials, whatever they are. So this is FF. Questions, comments, concerns so far? Okay. If there are none, now what we want to do, Vine, is we want to go ahead and we want to find the acceleration of our block. Yeah, you do. So how are we going to find the acceleration of the block? Someone other than Vine. In dynamics, everything starts from what equation? F net equals MA. F net equals MA. If you forgot the rest, you have a handy dandy little formula sheet that you should be ready to reference. Oh, here it is. Here's my formula sheet. We're in the unit on dynamics. The very first equation listed is F net equals MA. Friction's right there, gravity's right there. All of these are on your formula sheet. There is nothing for you to memorize. You do need to know that F net is equal to the sum of the forces in the direction of motion. So we've got a block presumably moving to the right. It has to be moving to the right. Friction is 23.89 to the left, and the applied force is 45 to the right. So this block has to be moving to the right. I need F net. I've got forces acting in opposite directions, so we have to go back to our diagram, and we have to add onto our diagram a direction that we want to call positive. Which way do you want to call positive? It doesn't matter. Ray Reed says to the right. That's what would make the most sense. And so now when I go into my F net equation, what is the sum of the forces going to be? How is it going to be written out now that we've defined to the right to be positive? What forces are acting left, right? FA and FF. FA is going to be positive, so it's going to be the applied force minus the force of friction is going to equal the mass of the object times the acceleration of the object. The applied force is 45. The force of friction we found already to be 23.89. The mass of the object accelerating is 3.75, and we're looking for A. The way you guys should lay these out is so that everything you have builds on the line that came below it. So what's the acceleration of the object? You're going to take 45, you're going to subtract 23.89, you're going to divide that result by 3.75, and you're going to get an acceleration of what? 5.629, so if I round that to 2 decimal places, I'm going to get 5.63 meters per second squared, which is actually a pretty impressive acceleration. if you're dragging an object across the tabletop. Here's a fun question for you. What if? Yeah, I'm not going to do it in here. So I'll ask you the question. What if we had found that this combination of 0.65 coefficient of friction and the normal force, what if this combination had provided a result larger than 45? What would that mean? What would it mean for the force of friction to be greater than the applied force? Either the object would be slowing down if it was already moving, or it wouldn't move at all. You're not pushing it hard enough to over that number, that bigger number than 45 would represent the maximum possible value for the force of friction. If you're pushing less than that, the thing's not going to move. What you need to remember here is that if you have a larger value than a larger force of friction than the applied force, friction is not going to make the thing move to the left. Friction only opposes motion, it does not cause motion. So those would be the two options. Yuli's either the thing's slowing down, or Ezra's the thing is not going to be moving at all. Good. Okay, two more examples. I've got a 0.2 kilogram, so 200 gram puck is pushed along a sheet of ice with a force of 0.240 newtons. If it moves at constant velocity, find the coefficient of friction between the puck and the sheet of ice. So we've got a sheet of ice. We know this. Sheets of ice are level. Making inclined sheets of ice is not an easy thing to do. So what's the free body diagram going to look like for our puck? FG is straight down, FN is straight up. There's going to be an FF and an FA. Okay, which direction do you want those to be in? FA to the right? Sure. You've got an applied force to the right, and we've got a value for that. We're told that the puck is pushed along a sheet of ice with a force of 0.240 newtons. So that's your applied force, 0.24 newtons. And force of friction is going to oppose motion, so force of friction is over here. There is some key language in here that gives us a value for the force of friction. What's the language in the problem that's going to give us the value for the force of friction? The fact that the object is moving at constant v means that the force of friction has to be what? 0.24. Oh, and I should put newtons over here too. If the object has constant velocity, it means that the forces are balanced in every direction. So FA and FF have to be the same. If we want to find the coefficient of friction, we're going to start up over here. The force of friction is equal to mu times Fn. So mu is going to equal the force of friction divided by Fn. So if I want the value for mu, we know the force of friction has to be 0.24 divided by, what's Fn? In this case, Fn is going to be equal to Fg, and Fg is going to equal mg. So let's go calculate it. M is 0.2 kilograms times 9.8, because presumably this sheet of ice is on Earth. If I want to throw you a real curveball, we could play hockey on the moon. That would be dumb. Oh, also really hard to get to. 0.2 times 9.8 is 1.96 newtons. So this is our value for Fg, which is also going to be equal to our value for Fn. So now I want to find mu, force of friction divided by Fn. I have my force of friction. I've now got my Fn. So what is the coefficient of friction for this puck moving across that ice? Ezra. Is it N there? What's the next digit? So 0.122, I'm cool with. Let's leave that way. That is the coefficient of friction between these surfaces. And look at this interesting result that we have not talked about yet. What are the units on this top value? The top value was what? Force of friction. What are the units on the force of friction? Newtons. This bottom value is the normal force. What are the units on the normal force? It's a force. All forces are measured in newtons. So if I take 0.24 newtons and I divide it by 1.96 newtons, what are the units on the coefficient of friction? Newtons divided by newtons, it's going to cancel. It means on a coefficient of friction, there are no units. It is a unitless value. It is just a statement of how two surfaces slide past each other. Comments, questions, concerns? Going once. Twice, thrice, sold. Okay, cool. One more example. A 1.1 kilogram textbook is held against a vertical wall with a force of 45 newtons. What is the coefficient of friction between the book and the wall? Let's demonstrate this one, shall we? I want a textbook that I don't mind. Actually, let's use one of mine over here. Let's grab this book. No, not that book. A book that I don't mind. Here, let's grab an old yearbook. Okay, the 2023, 2024 Abbey Senior Yearbook. Excuse me, we're going to take the textbook and we're holding it against the vertical wall. I'm pushing on this thing with a force of 45 newtons. What's the coefficient of friction between the book and the wall? So let's analyze this. What are the forces acting on the book? Gravity. Gravity's acting which way? Down, because if I let go, the thing's going to slide. Bless you. What other forces are acting on this thing? Yes. It applies when the surface is in contact with an object in any orientation. Which means there's a normal force which way? Normal force is always perpendicular to the surface. The surface goes up. So which way does the normal force have to go? This is actually getting surprisingly difficult. Yeah, the normal force is going to be coming off the wall this way. Because I'm pushing on the book with 45 newtons of force, but the book is not going into the wall. So if I'm pushing at 45, then the normal force has to be what? 45. There has to be something pushing against me, pushing on the book, because the book's not going anywhere, and I'm pushing on it. As soon as I start pushing on it, it falls. So that could be the only thing. If the object falls naturally on its own, friction is going to oppose motion. The motion of the book wants to be down, so as Kai just said, for those of you who didn't hear, the force of friction has to be up, backwards against gravity. Cool. So let's draw that out. My force was into the wall. That was my applied force. And because the book's not going into the wall, but the book is on a surface, there has to be a normal force pushing back out against me. Because the book wasn't moving into the wall or like rebounding off the wall, these two forces have to be equal. So FA is going to equal 45, and FN is going to equal 45. And both of those should have units of newtons. Someone said gravity was down. Gravity is always down. And someone else, Kai, you said, well, if this thing's not sliding down, there has to be a force opposing it. So that's got to be the force of friction opposing the downward motion of the book. So very different looking scenario than a horizontal surface, but the situation is the same. We've got, for a stationary object, we've got all these forces in balance. Held against implies that the thing's not accelerating. If the thing's not accelerating, Fn and Fa have to be equal, and what other pair of the force have to be equal? Ff and Fg. These two forces have to be equal. So if we want to go ahead and figure out what the coefficient of friction is between the wall and the book, we want the coefficient of friction between the wall and the book. So force of friction is equal to mu Fn. We want to find mu. So mu is going to equal the force of friction divided by the normal force. And we can start deducing some of these things. Fn is equal to Fa. So I'm going to get 45 newtons down here on the bottom. And the force of friction is equal to Fg. I don't know what Fg is, but we can calculate it relatively easily. Presumably we're on Earth. Fg is going to equal mg. The mass of the book is 1.1 kilos. And I'm going to have an acceleration due to gravity of 9.8. 1.1 times 9.8 is 10.78. So if these two are equal and opposite, if Fg is 10.78, means our force of friction is also 10.78 newtons, and now we can go ahead and shove this into this equation. Mu is equal to force of friction divided by Fn. Fn is 45 due to this argument over here. Force of friction is 10.78 due to this argument over here, which gives us a coefficient of friction of 0.24, and there are no units on the coefficient of friction. Comments, questions, concerns? I'll make one note here. This value is only going to be, because look where this value came from. This value came from the force of friction and Fg. These two are always going to be equal in this scenario. So Fg is dependent on the mass and gravity. So you're going to have a constant value for the friction here. Fn is always going to be equal to Fa. In this case, my Fa was 45. But if I wanted to, could I have pushed harder than 45 newtons? Yeah, I could have. And because even if I'm pushing harder, the object's still not going to go into the wall, which means my Fn would grow to meet the Fa. These two are always going to be equal unless the book finds itself being absorbed into the wall. So the only way that this is actually the coefficient of friction for these two surfaces is if what is true about that applied force. There has to be something true about that applied force. What's got to be true about that applied force? I'll demonstrate the book again. I push really hard, that Fm is going to get bigger, which means the coefficient of friction is going to change. It's going to get smaller. The only way for that coefficient of friction to be an accurate representation of these two surfaces is if I reduce my applied force to what? Not 0. Because if it's 0, the thing's definitely going to fall. Well, look, so who said 0? Daniel said you. Okay. So look at what happens here, Daniel. If I pull back a little bit, I'm still pushing on the wall, but now the book is sliding. I'm not making it slide, it's going down on its own. No, but you're getting warmer. There is going to be some minimum value here to keep the thing stationary. Whatever that minimum value is, in this case, this question is suggesting that that minimum value is 45. It doesn't state that. If you push too hard, you're going to get an inaccurate value for the coefficient of friction. If you push not hard enough, the thing's just going to fall. You need that minimum value of Fn. So I just want to make that clear here. Fa needs to be as small as possible and still the book, I could have said this probably shorter, but here we are, and still the book doesn't move. There is a minimum value for that force. At that point, you're going to get an accurate representation for the coefficient of friction. If you push too hard, you're not going to get an accurate representation. You don't push hard enough, the thing's going to slide down the wall. So this is friction. Something so simple that you've interacted with your whole life now has a whole lot more meaning. It's like my example back a couple weeks ago when the ex-girlfriend and I broke up over the magicness of the wind. This is yet another concept that I can break down for you. Friction becomes less magical, I'm sorry. Okay, so here's what I want you to do. I'll give you about 20 minutes and then I'm going to introduce the lab. I would like you to play with the following questions. There's a whole bunch here. I'm not going to get you to do all of them because that's a lot. One's cool, one's easy. We'll get you to do two. Two's nice. 1 and 2 are good. Let's do 4 and 5. Changing this from last year. Ooh, we like 6 and 7. Right now we've only skipped 3. We should skip another one. Ooh, but 8's good too. I'll do 8. We'll skip 9. We'll do 10. Takes that much to do that. What's the coefficient of friction? I want you to do that one. Yeah, we'll do 11 too. There's some implication here in some of these questions that I want to make really, really clear. in 10, 10C says how much force is needed to pull the toboggan if two 60-kilogram girls are sitting on it. What you're looking for is the minimum force. Minimum applied force is the implication of that question. Obviously, there are huge forces that you could apply to yank this toboggan around with these 60-kilogram girls on it. What's the smallest possible force needed to successfully pull these girls around? And the same thing is true in 11. That 5 Newton force to pull a 2-kilogram object along the ground, that's the minimum. This is the smallest possible force. And so the implication there, if that's the smallest possible force, it means this thing's not accelerating, but you're moving at constant velocity, which means this applied force is going to be related to the force of friction. How? If that is the smallest possible force to move the object, how is that going to be related to the force of friction? Sorry? I heard something. Nope, I'm being gaslit by the breeze. Well, I'll let you play with that idea. Those are the questions I want you to take a look at. Like I said, in about 20 minutes, I'll introduce to you the lab that you're going to do for me tomorrow. My TOC tomorrow is going to be Mrs. Peters' wife. Sorry, Mr. Peters' wife, Mrs. Peters. She's great, but she is not a physics teacher. So want to make things clear before I leave what tomorrow is going to look like for you guys. So there you go. See what you can do with the time you have. Let me know if you have any questions.